Hello and welcome to IET 301 Engineering Project Cost Analysis. In this video we're going to review and summarize Chapter 3. We're also going to quickly touch on the final concept out of Chapter 2, which is cash flow diagrams. This, as I mentioned, it was introduced in Chapter 2, however it's a better fit to toss it in here with the material for Chapter 3. It gives you a little more context to work with or understanding this material. So what we're going to do in this video is introduce these cash flow diagrams. Then we're going to go in and introduce the time value of money and what it means to be equivalent. When we finish that up, we're going to introduce simple and compound interest. For the majority of us, this will be a review of what we saw in pre-calculus. These same concepts are introduced here. We will be introducing these in a slightly more financial sense. The use of tables in economics is used extensively, therefore I'll introduce how to use these tables to determine the simple and compound, or the compound interest. And finally, we're going to introduce the present and future value of money. So to get started, I'm going to introduce you to these things known as cash flow diagrams. And as a motivating example, let's say that I want to go through and look at my salary since the year 2000. It's been pretty much up and down since that time, but I'm going to fill this out in what's known as a cash flow table. And as we know from our math classes, anything that we can put in a table, we can go through and likewise express in a graphical form. And that's what the cash flow diagram is. It's just a graphical representation of this tabular information. So when we're working with these cash flow tables, we have two columns. We have the time column and we have the cash flow column. So it turns out that I graduated with my engineering degree in 1996. So by the time that year 2000 came around, I was doing fairly well. So in 2000, I had an income of about $50,000. At the time I was single, so that was more than adequate to support me and my dog that I had at the time. Over the course of the next 3 years, I had several opportunities for promotion. So in 2001, I jumped up to about $58,000. In 2002, I moved from there up to about $65,000. And then as it turns out, in 2003, I only worked a partial year, so I dropped back down to right around $50,000. Now, in 2004, something interesting happened. I encountered for the first time since I graduated from college a negative cash flow associated with my income. Typically when we're talking about negative cash flows, we can either express those in red if we're conveniently using a spreadsheet application, or we can put them in parentheses to represent them as negative. If you are mathematically minded as I am, it's very tempting to put a negative sign out in front of here, but the more customary representation for negative cash flows is to use parentheses. Then in 2005, I had about a negative $35,000 income. 2006, I had a negative $30,000. 2007, I was back on the game. 2008, I was up at 49,000, and then finally in 2009, I was maintaining my salary of $49,000. Okay, so what we can see here is that we have a bunch of cash flows. Now, I've already mentioned that these three cash flows for 2004, 2005, 2006 were negative. Turns out that those were the years I was working on a master's degree. Therefore, I was, instead of having an income coming in, I was spending the money I had in savings to pay for my master's degree. So, with this tabular format set up, what we could do is go through and, instead of writing these out in, as years 2000, 2001, 2002, and so on and so forth, we could represent these as or in terms of a index year or an index time. And when we're going through, we can go through and just assume that the first time is occurring at in 2000. The second time, 2001, is occurring in the first year, second year, third year, fourth year, fifth year, sixth, seventh, eighth, and ninth. This saves us several things. First off, it removes the increment on time. For example, if we were saying that our time was January of 2000 and then a second occurrence occurring in July of 2000, that would become very cumbersome to represent. But if we just go through and represent these as time 0, 1, 2, 3, so on and so forth, then we can simplify the cash flow diagram and the contents of the cash flow table. So with that then, what we're going to do in creating a cash flow diagram is draw two axes, just like we would do in our math class. We're going to have an independent horizontal axis, which will represent our independent quantity, our time, and we'll go through and say that these times are set up based on our index value rather than the actual value. So 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And in order to represent a positive cash flow, we're going to draw an upward vector that it has approximately the magnitude that's expressed by the magnitudes of the quantity. So if this represents 50,000, then we'd have a magnitude slightly greater for 58,000, and finally a magnitude slightly greater than that to represent 65,000. And it's really not a bad idea, especially when you're doing these cash flow diagrams by hand, to include the magnitude at the end of the vector, just so that you know how much or what that's actually representing. And then in year 3, we are again at 50,000, and then we have several negative years. In this case, I'm not doing a real good job of approximating these because we know 30,000 should extend on down into here. That would be much more accurately plotted if you were using a software application of some sort. For those of you that are online, moving through the material, keep in mind that I posted a number of Excel tutorials. The tutorial, or one of the tutorials in chapter 2, specifically shows you how to create a cash flow diagram using Excel. So while this cash flow diagram is not overly sophisticated, it really does a good job of giving us a graphical sense of what's going on in this scenario. And finally, 49,000. And again, I kind of messed up my magnitude here. When you're going through and creating these by hand, I'd strongly advise you to use a ruler or a scale to draw in each of the axes and components nice and orthogonally. spend your time to write this out neatly. If you're producing these with Excel, then some of the niceness factor is taken care of for you. So just kind of keep that in mind. With this then, keep in mind that these cash flows always occur at the end of the year. So we can say that, well, we could actually say one of two things. Either that this $50,000 income occurs at the year end zero or at the beginning of year one, okay? So, and then finally this $58,000 occurs either at the end of year one or at the beginning of year two. And that's very important because it really gives us a sense for what this year zero income represents. So I hope this gives you a good idea of what a cash flow diagram is. It's really an important tool to use when understanding these different economic type of problems. It gives you a picture to work with. And with that, if you can draw out a picture of the cash flows in the particular problem you're working on, it just gives you a second way of understanding that scenario. And ultimately, if you think back to your math classes, that's the entire reason why you were forced to go through and graph and plot and everything else, is because you needed a second way of understanding those math problems. This does the same thing for us. Okay, so with that then, I will go ahead and jump right into Chapter 3. Chapter 3 discusses equivalence and interest. And to introduce this idea of equivalence, let's say that we have two options. Option number one is that right now I can receive a bonus for $10,000. Option two is that a year from now I can receive a $10,000 bonus. Which do you think I would probably choose? Most people are going to say, well, just given any kind of sense at all, you're going to choose to take the $10,000 today. Okay, well, why do you suppose that is? Primary reason why most people would choose to take the $10,000 today rather than the $10,000 a year from now is the prospect of being able to do something with it over the next year. Okay? This means that we expect this $10,000 we receive today to have some value to it today that it won't have a year from now, or that the $10,000 a year from now will not have. And this is the idea of interest. So interest is money paid to use someone else's money. Okay, and this expresses the time value of money. Everything you do in engineering economics comes back to this central principle. Everything that you can do with money over the course of some time period, you have to account for that time value of money. If you take out a loan today for $10,000 and pay it back over 5 years, it's not going to cost you $10,000 when it's said and done. it's going to cost you that $10,000 plus the accrued interest that the bank is going to charge you for using their money. So this is the central idea in this course, and for that matter in any economics course. When we go through and talk about this, we have several different types of interest that we can work with. And as I said, this is going to be a throwback to your pre-calc days, so it's going to look very familiar for you. The first type of interest that we have is what's known as simple interest. And this is nothing more than interest that is computed only on the original amount. Or their original principal, we could say. So if we go through and want to figure out what the future value is of some present value amount, we could say that the future value is equal to the present value plus the present value times the interest rate, which the book expresses as an I, times the time. Now, the book uses N to represent time, but you'll see here momentarily that that tends to lead to some confusion. They also go through and say that this is referred to as the number of payments, which makes a little bit more sense, but for the examples that I give, I will almost universally go through and use time as my variable. When you set up your spreadsheets using the 5-button method that is described in the textbook and in the tutorial videos, make sure that you're labeling it as they do, just so that it's consistent. If you go through and do that, and I go through and read the problem, I'm going to be, or grade the problem, I'm going to be looking at the exact same solution that you present as is presented in the homework. So, okay, so in this case, let's say that we have, as an example, a present value of $10,000. Okay, and we're going through and we're charged 8% interest over a over a 10-year loan. Okay, so in this case, what we would see is that we would have the future value of this purchase or of this or of this loan, or whatever the case is going to be the $10,000, which represents our principal or our present value, plus the $10,000 times the 8%, which we should express as a decimal. 0.08 is equivalent to 8% times the 10 years. So we see that we have $10,000 plus 10,000 times 0.08 times 10 is 0.8. So let's see, that would be 8,000 plus 10,000 would give us a value of $18,000. Okay, that means that if we're charged simple interest here, if we pay this loan back in 10 years from the day that we take it out, it's going to cost us $18,000 to pay back that loan. Now, while we're very seldom charged simple interest when buying a car or buying a house or anything else, this really does demonstrate to us the reason why banks exist. they charge these interest rates so that they receive a return on their investment that is represented by that loan that they give you. With this being the case then, you need to recognize that this $8,000 that you're paying in excess of the original loan balance is coming out of your pocket. So keep this in mind whenever you're considering taking out a loan or using your credit card or anything of this nature. One of the things that a course like this does for you, at least hopefully, is it makes you wiser consumers. Ultimately, you don't want to be the person that is running up $10,000, $20,000 worth of loans or consumer debt or whatever the case is, because ultimately that is money that not only you're having to pay back, but you're having to pay the associated interest on top of it. Okay, so the second type of interest that we commonly run into is what's known as compounded interest. And this is the much more common type of interest. It is interest that is periodically compounded, just like the name suggests. So let's say that we have that $10,000. So in the first year, or at the end of the first year, we take that $10,000 plus the $10,000 times 0.08%. And this would give us $10,000 plus $800 earned in that first year, or received in that first year for interest. So this would give us $10,800, too many zeros there, $10,800. In the second year then, we would not go through and calculate interest based on the original principal value, but the year-end principal value that is hanging out there. So what we would see then is that in the second year, we'd have $10,800 plus $10,800 times 0.08. And this would give us the next accrued or compounded value for our principal quantity. So in order to do this, we can see that one of the easiest ways to express this, if we wanted to factor out the 10,000, is we could express this as 10,000 times 1 plus 0.08, so 1 plus 0.08. And in the second year, we're going to be taking that quantity and multiplying it by the 1 plus 0.08 again. And in the third year, we're multiplying that by the 1.08 again, and so on and so forth. So ultimately, what we can do when we're expressing the future value in terms of the present value when dealing with compounded interest is say that the future value is equal to the present value times 1 plus the interest rate raised to the number of payment periods, T. Okay, so let's go through and take a look at this. If we go through and let's, as an example, say that we have a $5,000 loan that we take out, that represents our present value. We're calculating the future value. And we're dealing with the same 8% rate that we have been over a 10-year term. What we would see then is that over that 10-year term, we have $10,794 for our total repayment amount. If we were to go through and do that with simple interest, we would see that it turned out to be $9,000. Okay, you can see quite a difference here. just by compounding this, in this case, month or annually, we'd end up with $10,794 rather than $9,000 that we end up using simple interest. If we were to go through and look at a cash flow diagram associated with this, we'd see that in year 0, 1, 2, 9, 10, if this is a loan that we're receiving, in year 0, we would have a positive cash flow of $5,000. In year 10, we would have a negative cash flow of $10,794. This is assuming that you pay the loan back in one lump sum in year 10. Okay. Now, on the other hand, if this was an investment that we were making, then we would see that the $5,000 that we're investing would represent a negative cash flow, and in year 10 we would receive a positive cash flow of the $10,794. So I hope that kind of helps you. Okay, now with this provides us a great opportunity to introduce a much more compact way of representing this. And this is where the economics starts to kick in. Generally what we can do is, instead of having to go through and memorize an equation, and you'll recognize that this equation isn't particularly hard to memorize. Future value equals present value times 1 plus the interest rate to the time. And it's a pretty straightforward problem. Virtually everyone has seen this problem in one form or another before, so it's just not something that should take too many people a significant amount of time to learn. However, the issue is some of the later equations we'll be using become quite involved. And for that reason, if we can avoid memorizing the equations necessarily when we don't have to, that's what we're going to prefer to do. So in order to allow ourselves to avoid memorizing an equation, economics has developed a compact notation to represent this. And this is very similar to, or uses some of the same concepts that you run into in math. What they do is, they say that the future value of a investment is equal to the present value times the future value given the present value, the interest rate, and the time. Okay? This right here represents the dependent or independent quantities in the problem. You have the future value given the present value, you have the interest rate, and you have the time. So for our example, we would say that the future value is equal to the present value of $5,000 times the future value given the present value, the 8% interest we know, and the time we know to be 10 years. Now, this compact format is ideally suited to work well with tables. In fact, if you look in the appendix, I believe it is Appendix C. Let me verify this real quick for you. Yes, in Appendix C in your book, this Appendix C starts on page 599. You have an entire series of tables that can be used instead of the equation in order to solve this. So I have the interest rate table for 8% interest. This is out of your textbook. In this case, we see that we're dealing with an interest rate of 8%, so that falls from the compact notation that we're using. We're looking at the future value given the present value, so we look in this first column, and we look in the row that corresponds with our t equal to 10. So we can see that we're going down the future given present column till we get to row 10, and in row 10 we see that the multiplier is 2.19 or 159. So what this tells us is that the future value is equal to $5,000 times that multiplier from the table, 2.159, and then this gives us $10,794, exactly as we received before. It's very important to note that these tables are specifically set up for compounding interest rates. They do not work with the simple interest rates at all. But you can see that rather than having to punch in this equation into our calculator, we have essentially turned it into a simple multiplication problem by using the table. And this is one of the very valuable things with that table is once we know what we're looking for using this compact notation here, we can go to the table, pull out the multiplier from the table, plug it into our equation, and we have the job done. Okay, so I hope this helps you understand what's going on here. Ultimately, the more you become accustomed to using your tables, the better off you're going to be. For those of you that plan to take the Fundamental of Engineering exam as you near completion of your degree, this is where it's at. You are provided these tables in your reference book for the Fundamental of Engineering exam, and if you know how to use these tables, that portion of the exam is just in the bag. Okay, one final type of interest that we need to be introduced to, even though it really doesn't come up too often. Most wise consumers recognize the fallacy in this type of interest, and that's what's known as continuously compounded interest. And what continuously compounding interest means is that interest is always compounding. Whereas continuously compounding. That means that if we took out this $5,000 loan and we took it out under a continuously compounding interest rate, well, from moment to moment, the loan balance would increase. So for example, we might have $5,200 this instant, and then $5,200.02 this instant. It just continually compounds as time passes. If we take a look at the base equation that we ran into previously, we can say that the future value is equal to the present value times 1 plus the interest rate to the time. Well, let's say that we divide this time into. This would represent an annual compounding loan or investment. Okay, let's say that instead of annually compounding, we're going to compound every 6 months. In that case, what we would see is that the future value would equal the present value times 1 plus the interest rate divided by 2. We're going to take the annual interest rate, in the previous example it was 8%, and say over 6 months, the effective interest rate will be 4%. And since we're now seeing 2 payment periods per year, we're going to take 2 times the number of years. So if this was over a 5-year period or a 10-year period, we would double that because now we're looking at 2 compounding periods per year. Well, let's step this up a bit and say that instead of, so this is compounding every 6 months. If we were going to go through and follow the same logic and say that we were compounding monthly, we could say that now our interest rate is going to be divided by 12. So our 8% interest rate would correspond to a 0.75% interest rate. So in this case, we could say that our effective interest rate would be 1 plus I over 12. Well, where this 12 corresponds with the number of payment periods per year. And in this case, then we have 12 times the number of years that represents the term of this loan. In general, what we could say is that the future value is equal to the present value times 1 plus the interest rate over the number of compounding periods per year raised to the nt. So this is a general form for non-annual. Sorry about my spelling there. Compounding. You could also use this if you were, say, for whatever reason, compounding every other year. Then you would say that your n is going to equal 1/2, because in this case you're going to be accruing half the interest in a year, and then the number of payment periods would be 1/2 t. Okay, so it not only works for dividing a year into smaller fragments, but grouping larger blocks of time rather than just a year into the equation as well. One of the interesting things that happens here is that as n starts growing really, really big, say upwards of infinity, we see something really cool happen. This 1 plus I to the n raised to the n starts to approach e to the I. Okay? And just as an example, you can take your calculator. If you take your calculator, and let's say that your interest rate is 0.08%, so you can take 1 plus 0.08%, and let's say that just as a number, you want to compound this 8%, maybe 1,000,000 times per year. So we'll divide this by 1,000,000. Raised to the 1/1,000,000th power. Okay. Well, when you punch that into the calculator, it's going to be essentially the same as taking e to the 0.08. And you guys can try this just to confirm this. But what this allows us to do then is come up with an equation for continuously compounding interest. This states that if we had or want to determine the future value given a present value, we can take that present value times e to the it, and we have it. So this is a general form for a continuously compounding investment or loan. Okay, so with this being the case then, if we go through and if we wanted to go through and wait just a second here. If we wanted to go through and figure out how much interest would be accumulated given our $5,000 equation, we could very easily set this up and say that we have 5,000 times e to the 0.08 times the 10 years that we had. So we'd have $5,000 times e to the 0.08 times 10 is 0.8. And this would give us the continuously compounding interest or the principal at the end of that 10 years of this $5,000 when invested in a continuously compounding investment. As I mentioned before, your tables are not set up for continuously compounding interest. They are only set up for compounded investments. If you use the table, which you should be using the table all the time, what you're going to see is that whenever you set this up, you're going to use the tables to determine compounded interest, not simple interest, not continuously compounded interest, just regular compounded interest. Okay, so with that being the case then, we are at the end of chapter 3. And while this probably didn't go through and touch on every type of problem you're going to run into on the chapter 3 homework and chapter 3 quiz, it should give you a real good idea of what you expect to see or should expect to see in chapter 3. So our next video will be a summary of chapter 4, and when we get there, I'll get that posted for you just as soon as possible. And if you have any questions, again, just make sure that you give me a call or preferably drop me an email. Thanks a lot. Talk to you later.